Please go ahead.
Sorry, one technical issue.
Yeah.
No, it should be okay. Okay, so thank you for the nice introduction, Rachel, and thank you, the organizer, for this nice opportunity to present a bit of arithmetic homotopy. So I chose to start with kind of a provocative slide, which mentioned 4 a priori unrelated topics. One is number theory and Galois theory, which deal with the maximum probable extension of on top of all the L root of unity over Q, which is an anormal variable L. The other one is related to the geometry and is related with finding the field of definition of a generic curve of genus G with M mark point with additional L-level structures. The third one is a topological issue, which is to consider the mapping class group of surfaces, which act on the homology generator of the Riemann surface, to consider the kernel as sort of an approximation of this group, which is a Torelli group. And the last one is related to the mixed category of mixed motif, and in particular to the faithful action of the Soule cycle in the Tanaka group of the category, the RAM version. So obviously, this thing is related to Chris Rasmussen talk. I'm sorry for the handwriting now. This one is totally free. This one is related to the Torelli group, which is this IG, and the Johnson obstruction morphism topology, which is an important question. And this one is related, at least in the case of genus 0, to Ishii-san talk, and also to Sharifi previous work. So now the interesting thing is that if you consider this arithmetic homotopy approach, in fact you can relate all these 4 approaches by looking at some arithmetic invariant built in this context. So let me now begin a bit more explicitly, what is everything is about. So let's look at what I mean by arithmetic homotopy and ODA. So let's begin with the geometric context. So I consider MGM, which is the Q stack, algebraic stack over Q, the Limbaum form, of families of curves of genus G with M points. So objects are of this form. You have a base, you have a family. On top of every point, you have the curves CS, and then you have n section CI, which will mark the points on each curve. So this is the object we are interested in, this space. Okay. Now, as a solution, as a fine solution to a moduli problem, this stack comes with a universal curve. So there exists C over M. So I'm sorry, sometimes I will drop the G and the M because I'm a bit lazy, but maybe not now. Okay. What does it mean for this to be universal? It means that every time you have a curve C over S, which is a GM curve in space, then, which means that you have a morphism like this, then this curve can be realized as a fiber product over this universal curve, isomorphically. Okay? Now we can come to the homotopy part of the thing. So the homotopy means that I apply now the étale fundamental group. I choose the geometric base point. This will be its objective. Here I take I want to add thing. If I take the fiber of this morphism, what I obtain here is a curve over Q bar, which will be just a GM curve. Okay, I take also the fiber of metal. I have my geometric point, and this is in 2. Okay, what does it tell? What do we obtain out of that? Maybe. What we obtain is that we have the outer action of this guy. You select an element, you lift, you act on the kernel, and we obtain here what is called the universal monodromy representation, which is so pi 1 eta of m g m at a point, go acting on the other guy, so out, so I don't make a choice of the section, pi 1, and here I will take the maximum Proel quotient, so x, q bar, point, something. So this guy is a max Proel quotient. Okay, so that would be my universal monodromy Proel representation. I denote that psi, g, m, and l. Now we come with the arithmetic. So we have the geometry, we have the homotopy, now we have the arithmetic. The arithmetic is that this guy being defined over Q, when we apply the pi 1 functorially, we have a morphism which is surjective over the algebraic, the absolute Galois group or optional number, GQ, P. Okay. And we can now build two things. We can build a group, so G, G, M, L, yes, which will be the projection of the kernel of this guy. E, G, M, L, and we can build a field, which will be denoted by Q, L, G, M, which is the field stabilized by the Galois. So Q bar of G, G, M. Okay. So maybe a few remarks. So the first thing is that by definition, this guy will be related to B. So that will be the field of definition of curve of GM type with N-level structure, roughly saying. Another comment is, why is this thing universal? It's universal because as soon as you have a curve which is over Q, you have also an action of GQ on these things, well, and so you have something like this, and you have a commutative diagram every time you have X over Q, a GM curve. Okay, so essentially this is the arithmetic geometric context that we are dealing with here. Okay, now come not Oda's conjecture, but Oda's prediction. Which is, sorry, that this Q, G, M, L is in fact stable equal to Q03 L, so independent of G and M. Okay, so now another comment. As soon as you see this, and you remember the last talk of Ishii-san and of Rasmussen a few last week, then you see that this thing by ERA is related to R. Yes. And plus there is a bit of work on Sharifi, but it's nice. Okay. Yes. Okay. Another very quick remark maybe is that it's not Oda's original prediction. So the original Oda involved in fact a weight which you see is the previous talk of Ishii. So you have tower QL GM And why was this thing introduced is that somehow Oda's remarks that the outer representation, the original one, is too big. So by cutting it in some graded pieces, this makes the study, the question theoretically easier. But in fact, when you begin to work, it makes all the things technically harder. So today I will not talk about the weight version, but just the classical one, essentially because in my case, in the stack case, it's very difficult, and at least we could not succeed on controlling the k in our arithmetic parameters. Okay. The other comment, which is also important, is that the Oda's prediction was already solved. But the success of work, so let me just write the initial. So first by Matsumoto, first step Matsumoto in 1996. Then there is a work from Takao in 2012. Also some work from Ihara, Nakamura, Ueno, Takao, and I think I don't forget anyone. Each of them using different kind of technique. So there is some group theoretic thing, there is some red groups, there is some Lie algebra, and there is some arithmetic geometry, meaning GQ acting on pi 1 eta or something. So this arithmetic homotopy I mentioned and I'm dealing here with. So the conclusion is that it's not an easy problem, and the other conclusion is that this is in fact a kind of a motivating question in the field of arithmetic geometry, also because of the previous ramification I wrote on the blackboard on the other topic. Okay, so now let me jump to the stacky aspect. If I can switch the camera, I think I can, yes. So what do I mean by stacky Oda? So I already mentioned the fact that the construction deals with the universal curve, and the universal curves comes because we have a fine moduli problem, and we have a fine moduli problem because we don't have a solution over scheme but over stacks. But nevertheless, we can be more precise. So to make the thing ever more stacky, I will not consider MGM the previous one, where the points are fixed, the mark points are fixed, but the one where the mark points are permutable. So it's family of curve C over S, which are endowed with a Cartier divisor, which roughly is the sum of the previous section. Or you can just think about this as the previous MGM with the symmetry group action. Okay. What makes it stacky? What makes it stacky is that you can build what is called the stack inertia, which is I M x bar, where x bar is the geometric point. This guy can be identified or thought as the automorphism group of the curve represented by x bar. Yes. It is obtained as a two-fiber product. So it's really a stacky thing. Okay. And because we deal with arithmetic property of étale fundamental group, what is important for us is that it goes into the étale fundamental group of the modular stack of curves taken over the bar. And I put the geometric terms. Okay, so this is the origin of stacky in this case. So later I will call that G. So because it's the automorphism of a Riemann surface, it's also a finite group. Okay, this is all you have to know about this. So now for the next step of the rest of the talk, I will fix the group G to be cyclic. So I morph it to Z over NZ. And what you can show is that there exists a certain kind of action of the absolute Galois group of rational number. So there is a Galois action on these stacks, on all these inertial stacks, that is a constant over the irreducible components of the following space of what I will call MG, so GM also as before, whose objects are family of curves C over S, where you ensure that each of them contains a group G. So this is called G special loci. It's special because you ensure that all the objects have a special kind of automorphism. This is a result that we had with Sylvain in many steps between 2015 and 22. So, yes. And my last comment is, how do we understand this constant over the irreducible component? Is essentially you have an irreducible component, you have a point, on top of that you have some IM of this point, then you can move this point, another point here, always the component. And what the Galois action will do is that it will move along the component this point to this point, so this group to this group by conjugacy, because it's inside the pi 1, right? The GQ action is here. And it will change the power of the generator of this guy, because we assume that it's a cyclical. So maybe I can write a very short example to make things a bit more concrete. I need 2. If I take the example of genus 0 curve, so I take M0, M, I take the group G to be of order M, same number of mark points, and I take gamma to be a generator. Then, what is the pi 1 of this guy, of the geometric one, on which we have a Galois action? We know that it is isomorphic to profinite compression of the blood groups with M strands quotiented by 2 relation, which I will not write. And this allows us to express this gamma. So these are generated by the classical R-team generator. So this guy, you can compute that it's equal as sigma 1, sigma 2, blah, 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 sigma minus 1. So we have some explicit computation. And the action, so if I take the Galois element on this gamma, it will just be given by, remember, I transport the inertia group by some element, and I just raise the power. Well, this guy is a cyclotometer actor. Okay, this is the meaning of this Galois action result. Another comment is, what are the irreducible components? You can describe, we have a way to describe that, of MG. That would be what we call MG, so maybe here we have to assume that it's cyclic. Car, whereas car are just the ramification data, the geometric one. So you have C, which belongs to this guy, U quotient by gamma, which means that you have inertia data, yes, of the base, this is pi, and the car will just be all the ramification data, the geometric one that you obtain here. Somehow. Okay, so we have also kind of a combinatorial way to describe the irreducible components, which we know have a very interesting and very rigid kind of Galois action or arithmetic. Okay, so now we can reach ODA. So we have also some universal monodromy organization. can show. So I have, okay, my notation is the following. So this guy, this time I go from pi1 eta of m gamma kr. So there is a g and m before with a geometric point. This I call the psi. I go acting on the pi1 max pro L of a curve CQ bar, always yes. I can also define so the question of other special loci, say, which is, you can guess, is the field Q, L, G, M, gamma, Kr. So we need all these parameters defined as the fixed field by, as before, the projection over on the absolute Galois group of the kernel of this universal moduli representation, independent of G, M, gamma, N, K. Okay. So, maybe, yes, two remarks. The first remark is that if we have G equal to 1, we recover classical order. The second remark is, why should that be true? So if you think about it, you may believe in the previous case that maybe there is a stabilization of the field because we just have curves with a bit of rigidification by adding this L-level structure. Now if you look at this situation, we have a stacky things, we take some very weird subspecial loci, we take the usable component, and we have many parameters. We make gamma cyclic to vary in top of G of M, and also the Ravis data. So there is a priori no reason why this thing should be true, and in fact it is. I mean, there is a bit of reason, but it's a bit twisted. So I'm just in my blackboard. And in fact, this is the results we obtained with several figures. This is joint work. Is that yes, other special loci holds. So I think we did that in 24. So other special loci hold. So yes, we have to take. Okay. Or G isomorphic to Z over LZ and L prime bigger than 5, I think. So Q, G, M, how do I raise that? Q, G, M, L, gamma, KR is equal to the same Q03 as before. Okay. So, how normal? The next goal will be for me to show you a bit what things are involved to establish this result, because I think there are some nice mathematics with classical techniques, but also with techniques which are possible only because we deal with the stack structure of the space. So the idea essentially will be to use a G quotient to move between the stratas and making a G and M to vary by quotient. Yes. It looks simple like this, but you will see that it's a bit tricky somehow. So from GM to G prime, a lower dimensional strata in the middle space. Okay? So for that, I will use some kind of a correspondence. So I consider M, G, M, any G. I take in fact the normalization of this guy. Why do we need this? Because it means that we fix a G action. This morphism is fixed over the curve, which means that we have a forgetful morphism, which goes, you just forget about the G action on the object. It goes to the bracket, sorry, M, G, M. But we also have the G quotient, which goes to M, G prime, M prime, so yes, M prime, and maybe the group of objects is generally bigger than what we have fixed before, so maybe there is some kind of a small group which act on all the objects of this new C. Okay, what does it give for order problem? It gives the following. It gives that, use color, we have first QGM, which we have then an extension to QGM of QGKR. Then you can show that this thing is a subfield of QGM of G. Now we have the quotient, so we also have QG prime and prime. Here we go into QG prime and prime delta G. You can show that you have also something here, and because we have a nice result from Nakamura, we know that both of them, I mean, any of them, contain already Q03. So this is Nakamura. Same result. Yes. So now if you want to show that, yes, we, that this extension of field is independent of GM, all these fields are independent of GM, we need just to close the loop by putting Q03 at the end. So the goal that we have to achieve will be to show that there exists a certain curve C, so that we can take QC, the previous field, which contain Q03. So all the goal will be this and that. Okay. Okay, I think I can just use the other method. Okay. So essentially there will be two cases which are both interesting. One is when the module stack of curve is proper, meaning that the dimension of this thing is given by, so proper means only a point, the dimension of this thing is given by the dimension of the quotient, and this means that here we have 0,3. Yes. And the other case will be when we can deform things, and in a way it's not a defect, it's a feature, because this is what we will use, we will build a family, so that we can control the irreducible components in terms of Q03 and then glue everything together. So there is a geometry and there is an arithmetic. Okay, so before that, of course, you can show that this guy is an isomorphism. For doing that, you have to show that when you go to the Poiret completion, the morphism between pi of x into GM and the quotient. So I'm lost in notation. Yes, okay. So C into the pi1 of L, C mod G is still into. So this is what forces the assumption to take G equal to D over LZ. This is an unabelian stiffness property. Yes. So, yes. So the isomorphism was not necessary for our goal, but it's a nice thing to. It tells a bit more. I'm sorry. Okay. Then I want to show you some examples. As I said, when mg and gamma kr is just a point, meaning when the quotient has been measured 0, so is 0.3. So what do? We must build some explicit model. And we have one, so we take, so there is, as always, geometry, Galois action, and a bit of work. Okay. So, we take the following curve, 3R, which is, look like this. We have some genius, we have some mark point, we have an explicit equation for this guy, so it's irrationally equivalent to this model, y minus 1 equal x L. So this thing is ZL over this over phi 1 minus 3 points. So phi 1 minus 3 points is what will give you the Q03. So we just have this, 1, 2, 3, essentially. Now we must look at a special kind of Galois action. So here we will use some, which is called a tangential vice point, and we use the so-called Delling one. So if you have a missing point, you can think about that as the way to take a loop in a tangential way to 0, for example. And 0, 1 means you move in the direction of 0, 1. Okay. So you have a tangential vice point. You also define here some TIG tangential place points on the different component of CR. These things, I don't give you the detail, but it defines some lift of the outer Galois action. So you have an action of Galois without the inner automorphism on the eta phi 1 of the object here. Write everything. Here defines a similar thing. Automorphism, blah, blah, blah. You have a morphism here. This is equal. And because you did that using tangential place point and lift of all these things is compatible, meaning that remember that you want to control the kernel of the Galois action essentially. So means that the kernel here, the kernel of, so if I call that phi01 and phi t, the kernel of phi t is inside, is controlled by the kernel of pt of phi. The other way around. The kernel of phi t is controlled by the kernel of phi 0. Okay. Which means that you have q of 0, 3, which contain, this is the other way around, I'm sorry, let me just check quickly. So this is it. Yes, in fact you can show that it's equal to q of c, and where c is the curve here. Okay, so this is a kind of game. So the input is we have some specific model, we define some compatible Galois action by some tangential vice point, which give a lift of the outer action. We can control the kernel by a bit of work, and then we have equality of the field extension. I'm put the M here. Okay. So this is a proper case. Now, what happened for the generic case? Essentially, we use the proper case and we glue things up. So to do that in a way that is compatible with the fundamental group and the Galois action, we do that using Grothendieck theory and formal deformation. So what is the GQ action? And the deformation theory, how does it work? So, we build the following. So we build a specific family. A specific family X over S, where you have base, you have a generic point, you have a special point, you have the generic fiber, which is the smooth things. So this is the thing we want to study, the generic fiber, or the pi 1 off. Yes. You have a family, here you have special fiber, which will be isomorphic to a certain x naught that we will build. Yes. Which may look like this. So it's singular, it's stable. You have mark point. Okay. Then you have some genus. This guy has different irreducible components. So x0, 1, x0, 3, and so on. Okay. And how do we build this family? We build it formally, using formal scheme. So you can think about this as the base is a formal scheme over K of Q. You have the parameter deformation Q here. We have, okay, doesn't work. We have our previous curve. So this is here Q equals 0. And we have, in fact, a formal neighborhood of this, of the singular object. Choc. So, which means that around the parameter, we have a smooth object. You can think about it like this. Okay. With the property that we can access to the different parts of, to the different irreducible component of the singular part, also using this formal approach. Okay. So now we want to do that. I said that it's compatible with the pi 1 and the Galois. So one condition is that the irreducible component and the mark point are a normal crossing divisor over X, which means that we can apply Grothendieck-Müller theory explicitly on this model that I will show you later, so that yes, the pi 1 of the formal guy for a certain tangential base point mu. Now it's not mystery anymore for you because you already saw what is a tangential base point. Is the same as the original family X that we are interested in, which is the same as the original pi 1 of the generic fiber minus the points. Always with respect to this tangential base point. Okay. Now we have the Galois thing. So what happened in terms of the Galois thing? We have the action of the Galois group of a certain K over this thing. And the way it works is that the Galois action on each irreducible pi 1 of component, so yes, irreducible component of this guy, control the same thing on the pi 1 d lambda x lambda mu. Yes, let me be a bit more precise. And then I can write TIG, where the TIG will be the tangential base point that we defined before. Because this guy will be a cover of pi 1 minus 3 points, this guy will be controlled by the arithmetic of the projective line minus 0, 1 and infinity, as I tried to illustrate before. And the outcome of that will be that yes, the field stable for these things will contain, it's not very nice, QL of 0. Okay? So now let me glue the build object. So this is maybe what I found interesting in this theory, is that you have very general formalism. This is LGR1, this is Grothendieck theory. This is some very abstract theory, but the goal is to find explicit model and to make it work. Yes. One reason, for example, we could not extend this result to Z over L to the N is because we have to find another model. So how do I find the model? This, I told you, by gluing something. So the thing that I glue is something of genus 0 with some ramification point in some mark point. So these are ramification point and this is mark point. Okay, so this is one object. So here we have a lot of ramification, but we don't have genus. And the other one is the opposite. We have some genus. And here we have a lot of mark points, but we have no genus. And here we have we need some ramification to glue. Because with glue point, we have the ramification. Otherwise, we cannot. But we have some genus. Okay. So this is an object formally. This theoretical component x lambda over k or t. Then you glue, for example, these two objects like this. So you have 1, 2, and maybe 3. Yes, and then 1, 2, 3, and 1, 1. So this is an object x mu over k, and this time I need two parameters, t1, t2. Yes. So formally, you have to remember that this is as if we had some kind of formal neighborhood of the degenerated object. Yes. Okay. And then we build everything together. Maybe this way. 1, 2, 3. 1, 2. 1, 2. Then we do like this. 1, 2, 3. Yes. Then we have the other one. 1, 2, 3. 1, 2, 3. And here I need, yes, I glue these two one together, and here I glue this one together, and I do that many times, so that I obtain the formal object that I was looking for before. Okay. In such a way that this guy is z over lz over of pi 1 minus 0, 1 infinity there. Meaning only some projective line minus 3 points glued together. Okay. What happens with these different parameters, t, t1, t2, and so on, happens the following is, it's a way to control. So it's not only a geometric thing to make a family, it's also a way to control the GKH. So this is what we define this mu tangential base point. By that I mean that you have, so you have the formal spectrum K, T. So this guy is a T over an irreducible component x lambda. Yes, you can send it to x of mu. You just follow this thing essentially. Okay. So the irreducible component of the degenerated one. This guy is a subthing of the big guy. Then you also have the formal version of lambda. So it goes like this. In the middle, you factorize by this k of t1, t2. Yes. And then you go like this, and you go like this. So the meaning is essentially that you have a mu tangential base point given by this morphism here. But this morphism is also compatible with the TIG morphism, which give you the link tangential base point on the projective line minus 3 point. And it's all done in a way that when you deform this T, you also deform the T1 and the T2. And of course, you do that anytime you want. One parameter will deform all the other parameters at once. This is essentially the way it works. And so maybe this is the conclusion is, yes, the outcome of this is that you have a mu tangential base point on the x0 that I defined before. This tangential base point is sent by construction to the 0,1 Deligne tangential base point over z quotient, the projective line is 0,1 infinity. And then by playing the same game as before, you obtain what I wrote before, which is that the field invariant QL of this generic fiber is contained in the Q0. Okay, so I think I used all my time. Maybe I can finish by a few comments. Yes. So the two comments are, first, this is very frustrating because as an input we use the previous result of Nakamura to have Q03 inside all the field extension. Can we bypass this construction, which is also difficult? We could not do it. We tried different type of quotient, we tried some other kind of deformation, we tried some group theoretic approach using mapping class group and rank group, and yes, we could not find a way to shortcut this. So it's a bit frustrating because it's not a 100% new proof of ODA special, which use only the stack arithmetic. We still rely on the previous result of Nakamura. Now the other comment would be, yes, maybe I will stop here in fact, because otherwise I will go into the Johnson morphism, it's a bit too far. Okay, so I think I used all my time, so I will stop here.
Thank you. Thank you for that wonderful talk. Would anyone like to ask a question? Maybe I can start with one. So when you're doing these deformations and you have the singular points, do you need,
Yes.
is there a sort of a radius or of the annuli that you need to work with, or does that not really matter?
Ah, I see. Yes, I see what you mean. So, in fact, okay, so the way I understand your question is, if you take a main surface with mark points, yes, your question is, the way to obtain this stable curve is to take some simple closed curve and to make it shrink, if I have the topological model in mind. And the annulus that you mentioned is some kind of the distance between these shrunken things, somehow, or how you can glue again together when you go back. This thing.
Yeah.
So in fact, you can be, it doesn't matter. So the short answer is it doesn't matter. It doesn't matter because we use this Q formal neighborhood. So it means that we have all the smallest neighborhood as small as we want around this simple closed curve. You can even be more precise because if we go from X algebraic to X analytic, yes, then the Q parameter that you have here is a deformation, which is when you Q equals 0, cut the surface, yes, will be realized really as an analytic rotation of exponential d something. I want to say maybe times Q, yes, meaning the bigger the Q, the bigger the rotation around this missing thing, yes, and the smaller the Q when we reach the singularity, the smaller the rotation. So when we glue, we really glue on any formal on any small neighborhood around these things. I don't know if it's. Yes.
Yeah, thank you. See, would anyone else like to ask a question? Well, great. Let's thank Benjamin again.
Thank you very much. It was a pleasure.
And this is our last talk this spring, and we will start again in August or September. Have a wonderful summer.